Greetings everybody, and welcome to the fourth installment of our example with polar coordinates. So in this problem, what we're asked to do is find the exact area inside the curve r is equal to 1 plus cosine of theta, and outside of the curve r is equal to cosine of theta. So let's see if we can figure out what these two graphs are actually looking like. So let's go over to GeoGebra and see what happens. Greetings everybody, welcome to example 4 of polar coordinates. So in this problem, what we're asked to do is to find the exact area inside the curve r is equal to 1 plus cosine theta, and outside the curve r is equal to cosine theta. So as always, let's go over to GeoGebra and take a look at what these curves actually look like. So what we have is the blue curve, which is going to be our cardioid of r is equal to 1 plus cosine theta. And then on the inside, we have just our regular circle where we have r is equal to cosine theta. And so what we want to do then is to find the area between these two curves. Well, one thing, when we retrace those curves out, we really have kind of different areas, or we have different values for the interval of of parameterization for these curves. For our curve r is equal to 1 plus cosine of theta, what we actually have there is that theta is going to be in between 2 pi and 0. Whereas for our r equal to cosine of theta, that one, we get the entire curve traced out using just the interval theta going from 0 over to pi. And so for the area, what we then really have is just the difference between these two areas. So let's calculate that and see what we have. For the area inside the cardioid, we have a 1/2 the integral from 0 to 2 pi of r squared, and our r squared looks like a 1 plus cosine of theta, and that squared d theta. Well, if we expand that, then we've got our integral from 0 to 2 pi of 1 plus 2 cosine of theta plus cosine squared of theta. And of course, we use our power reduction formula for our cosine squared, so that we have the integral from 0 to 2 pi of 1 plus 2 cosine of theta plus a 1/2 plus a 1/2 cosine of 2 theta d theta. So this is going to give us a 1/2. 1 plus 1/2 gives us 3/2, so we have a 3/2 theta plus the integral of 2 cosine was going to be 2 sine. And then our integral of cosine of 2 theta just becomes a 1/4 sine of 2 theta. And we have this evaluated between 0 and 2 pi. So when we plug in those numbers, what we then have is a 1/2 times, we plug in a 2 pi, our sine of 2 pi, sine of 4 pi will both be 0. So we have a 3/2 times 2 pi. And then when we plug in 0, it is 0. So we just have our 2's canceling, and so we get a value of 3 pi over 2 for the area of the cardioid. Now let's calculate the area for that circle. So for the area of the circle, remember that one is going to be parameterized from 0 up to pi. So we have 1/2 r squared is just going to be our cosine of theta squared d theta. So again, using our power reduction formula, we have the integral from 0 up to pi of 1/2 plus a 1/2 cosine of 2 theta d theta. So we have a 1/2 times a 1/2 theta plus a 1/4 sine of 2 theta, evaluated from our integral, evaluated at 0 and pi. So we have values 1/2. We plug in pi, and we have our pi over 2. Sine of 2 pi gives us 0. We plug in 0, and we get 0. And so we have just a value of pi over 4. And so for the area outside the circle and inside our cardioid, we have the area of the shaded region is then going to be the area of our cardioid of 3 pi over 2, and then minus the area of our circle, which was pi over 4. And so what we have then for a final answer is 5 pi over 4. So I hope you've enjoyed this. It's been informative, and I will see you guys in the next example.